Hello, this module will discuss different types of number systems for your week 7 and 8 learning module. Let's look into the objectives of this module. The first one is to explain the different types of number system, to identify and define unit, number, base, or radix, positional notation, and the most and least significant digits as they relate to decimal, binary, octal, and hexadecimal number systems. And the last is to implement basic skill in number system conversion such as binary to octal, decimal to binary, and vice versa. Now, in computer system, the only language that the computer can understand is or should be written in a binary system. So there are actually four types of number systems which we can represent in computer system. The first one, and as discussed during the previous modules, we have the binary number system. From the word binary, the base is equal to 2. The digits used is 0 and 1. And of course, the next one is the octal number system. Since that is octal, the base is 8, or base or radix. The digits used from 0 to 7. So total, we have 8 digits. In the hexadecimal number system, we have hexadecimal, we have 16. The digits used is from 0 to 9, and that is A to F, which represents from 10 to 15 digits in the decimal. And of course, the other one is the decimal number system, which is no longer written here since we all use decimal number system from day to day. The first number system that we are going to discuss is the binary number system. In the binary number system, the rightmost digit is called the least significant bit, and the leftmost digit is called the most significant bit, as shown in this figure. So, for example, we have binary digit 11010. The least significant bit is 0, and the most significant bit is 1. Nabanggit natin kanina that the binary system only uses the digits 0 and 1. Like decimal number system, our binary number system is also uses the positional value system. So in this case, we have the least significant bit, we have the position equal to 0. And of course, followed by the position 1, position 2, position 3, position 4, and position 5. So meaning to say that the least significant bit is at position 0, followed by position 1, position 2, position 3, position 4. Now, we can see here that the radix, or we have here the base of 2, since our binary number system only use 2 digits. Okay. This positional value is used to convert our binary digit into decimal value. For example, represent the binary number 10101 in decimal. So we all know that our binary is at base 2, our decimal is at base 10. So the problem is asking to convert the number in base 2 into number in base 10. So how are we going to do that? Now we have steps using the positional value. So the first, or the least significant bit is at position 0. We have here position 1, 2, position 3, and position 4. Now, we are going to multiply each digit into its positional value. We have here, this digit is 1, so we have 1, multiply it by 2 raised to its positional value, that is equal to 0. Then next, we have 0, multiplied by 2 raised to its positional value, which is 1. Then another 1, we have 1 times 2 raised to its position, which is 2, until we have this most significant bit, we have 1 multiplied by 2 raised to its position. Now, if we are going to get that one, we have 1 times 2 raised to 4, we have 16. 0 times 2 raised to 3, that will be 0. 1 times 2 raised to 4 is 4. And 0 times 2 raised to 1 is 0. And then we have 1 times 2 raised to 0 is equal to 1. So, adding it up, we have the decimal value equal to 21. Therefore, the binary number 10101 is equivalent to 21 decimal. The next number system that we're going to discuss is the octal number system. If our decimal number system has 10 digits, our binary has 2 digits. Now, our octal number system, we have 8 digits from 0 up to 7. So like our binary and decimal number system, our octal number system is also positional value system where in digits are expressed in powers of 8 as shown in this figure. So lagi tatandaan yung pinaka rightmost digit is what we call the least significant digit, and yung pinaka leftmost digit is what we call the most significant digit. I term it as a digit because this is already an octal. So like our decimal and binary, we also start as the position 0, then followed by 1, 2, and increasing in number. Now example, we are going to convert an octal number into its equivalent decimal number system. So we have the following step. So in our example, we have 12570 base 8 into equivalent base 10. So we have here our step. So the rule here is we are just going to multiply each digit into its equivalent power of 8. So in this example, if I'm going to write it in this way, 12570, this digit, we are going to multiply it by 0 times 8 raised to its position, that is 0. We have here 7 times 8, we have 1. And then we continue, we have 5 times 8 raised to its position, we're in 2. Then next we have 2 times 8 raised to position 3. Then 1 times 8 raised to its position 4. So we get the values. We have here 1 times 8 raised to 4, we have 1496. We have 2 times 8 raised to 3, we have 1024. 5 times 8 raised to 2, we have 320. 7 times 8 raised to 1 is 56. And of course 0 times 8 raised to 0 is we have 0. Then we get the sum. So the equivalent value for 125070 base 8, this is equivalent to 5496 base 10. Now the last number system that we are going to discuss is the hexadecimal number system. The hexadecimal number system has 16 symbols or 16 digits. We have 0 to 9, and we have A to F, where A is equal to 10 and B is equal to 11. And of course, we have until F, where F is equal to the value 15. Now, like the other number system, hexadecimal system is also represented in a positional value system, wherein the least significant digit begins at 0 and the most significant digit is raised to n, or the position n. In this case, in this figure, we only have 6 digits, so the most significant bit is at the position 5. Now let's take a look at this example. We have the hexadecimal number 19FDE. We said that E is 14, D is 13, F is 15. So we are going to calculate the equivalent decimal of this hexadecimal value like our octal. So if I am going to rewrite it here, you have 19FDE. So the least significant begins at position 0, 1, 2, 3, and then 4. So we multiply E. E is 14, then that is 14 times its positional value, that is 16 raised to 0. We have here D is 13 times 16 raised to its position. We have F, that is 15 times 16 raised to 2. We have 9 times 16 raised to 3. And then we have 1 times 16 raised to 4. So having that, we can say that the value, computing these values, we have 65, 53, 6, then 36, 84, 4, 38, 40, 208, and 14 base 10. So summing it up, we have the hexadecimal 19FDE that is equivalent to our decimal 106462 base 10. Now we are going to take a look at the number system conversion from decimal to binary, decimal to octal, decimal to hexadecimal, and other number systems to each other. So from binary to octal, binary to hexadecimal. So what we have finished is from uh, binary to decimal, octal to decimal, and hexadecimal to decimal. For now, we are going to look into decimal, converting it into its equivalent under number system. Now we are going to take a look how to convert decimal number into its equivalent binary number. Now, to convert decimal value into binary value, we are going to do successive division. So wherein we're going to divide the given number into the radix of the number we want to convert into. So for example, here the decimal to binary, we want to convert base 10 into base 2. So we are going to divide the number in base 10 into the radix of the number we want to convert into. So for our case, we have the base 2. Now, if we are going to convert decimal value 43 into its equivalent binary number, so we are going to divide 43 divided by 2, we are going to have 21, and we only consider the remainder. Now, to get the remainder, we are going to multiply the decimal point into the radix of our divisor. For example, we have 43 divided by 2, that is 21.5. Okay, so we get 0.5, multiply it by the radix, which is 2, then we have equal the remainder equal to 1. So that is equal to 1. Now this is simple since we only have 1 and 0. Our divisor is only 2, but we will appreciate it afterwards when we go to decimal, hexadecimal and octal. Now we continue our successive division until such time the remainder is equal to 0. So we have 21 divided by 2, that is equal to 10, remainder 1. Then 10 divided by 2 equal to 5, remainder 0. We have 5 divided by 2, that is 2, remainder 1. Then we have 2 divided by 2 is equal to 1, remainder 0. And 1 divided by 2, that is equal to 0, remainder 1. So the next thing we need to do is to arrange it upwards. So we have 1, 0, 1, 0, 1, 1, base 2. So therefore, our decimal 43 is equivalent to 1, 0, 1, 0, 1, 1, base 2. So take note, we just to divide the decimal number by the radix of the number we want to convert into. So in our first example, that is 2. Okay, next, moving forward, we have decimal to octal. Just the same, we are going to divide the number by the base. So let's take a look. For example, we have this number for decimal number 473. So we divide the number, okay, we divide the number 473. We have 59, remainder 1. Then we have also 59 divided by 8. We have 7, remainder 3. And we have 7 divided by 8, that is 0, remainder 7. And we arrange it upwards. So we have 7, 70, 731, that is base 8. So we have 423 base 10, that is equivalent to 731 base 8. So, ulitin lang natin, i-divide lang yung decimal number doon sa radix ng gusto nating pag-convert. Kung gusto mo decimal to octal, you divide the decimal by 8. Pag gusto mo ng binary, you divide the decimal by 2. So kung gusto mo other bases, Other bases, you divide it by that base. For example, you need base 21. So the decimal, you divide it by 21. So the last is to convert decimal to hexadecimal. As I mentioned, you divide the number by the base. So in this case, our base is 16 since we have hexadecimal. So 423 divided by 16, that is 26, remainder 7. Then 26 divided by 16, that is equal to 1, remainder 10, or this is remainder 10, or equivalent is A. Then we have 1 divided by 16, that is 0, remainder 1. Then again, arrange it upwards. We have 423 base 10 is equivalent to 1A7 base 16. Ulitin lang natin. For example, you want to have decimal into a base which is not standard. For example, base 9. So you divide the decimal number by the radix 9. So example, if we have 23 base 10, you want it to convert it to n base 9, then we have 23 divided by 9. Okay, so that is equal to 2, remainder 5. Then we divide 2 divided by 9, that is 0, remainder 2. Alright, so we arrange it. That is 23 base 10 is equivalent to 25 base 9. So, ganun lang kasimple. Next, we can also convert binary to octal, vice versa. To convert the binary number to octal number, these are the steps to be followed. Or in other words, simply say, you are just going to group the binary number system in by threes, pag octal by threes. Since 2 raised to 3 is equal to 8. You just group it by 3, starting of course from the least significant bit. So here our least significant bit is the rightmost and our most is our leftmost. So divide it or group it into 3, 3, 3, 3. Ito, dalawa lang. Lagyan lang natin siya ng 0 para maging 3. Since in decimal number system, if this is 25, lagyan mo ng 0 dito, this is still 25. Now, the octal and binary equivalent, of course, we have 0, 0, 0, 0. We have 1, that is 0, 0, 1, 2, 3, we have 0, 1, 1, 4, we have 1, 0, 0, 5, we have 1, 0. Paano natin nagawa? Nakuha yun. So, remember that pagkuha natin yun, positional value, this is 0, 1, and 2. Right? So, kung 1, 1, 1, we have here 1 times 2 raised to 0. We have 1 times 2 raised to 1. We have 1 times 2 raised to 2. So, the equivalent value ng mga to, we have 1, 2, then 4. Right? So, kung 1 mo, dapat 0, 0, 1. So, 1, 2, 4, position value natin, and yung equivalent natin, 1, 2, 4. So, kung 1 lang yan, i-add mo, that will give us only 1. 0, 1, 0, i-add mo yan, magiging 2. 0, 1, 1, that is 2 plus 1, magiging 3. That is 1, 0, 0, 4 plus 0 plus 0, that is. So, I guess you get the point. Okay. Kung convert natin based on this table, we have 1, 0, 1, that is 1, 2, 4, that is 1 plus 4, that is equal to 5. 4 to 1, that is 2, that is 4 to 1, that is 6, 4 to 1, that is 2. So, yung equivalent ng binary na to sa octal ay this one, 26, 25. So, we can also convert binary into hexadecimal. So, like binary to octal, we are going to use also the grouping. But in this case, since we have to convert binary to hexadecimal, we are going to group it by 4. Since 2 raised to 4, we have 16, and hexadecimal is base 16. So, starting from the least significant, we have this by 4. Okay. So, again, if you are going to have the positional value, that is, this is 1, 2, 4, 8. 1, 2, 4, 8, 1, 2, 4, 8. So how did we get 1, 2, 4, 8? So if we have again 1, 1, 1, 1, we multiply this by 1 times 2 raised to 0, that is equivalent to 1. This 1 times 2 raised to 1, that is equivalent to 2. Here we have 1 times 2 raised to 2, we have 4. And here we have 1 times 2 raised to 3, we have 8. So that is why we can simply say that this is 1, 2, 4, and 8. So adding the only ones because 0 multiplied by any number is 0. So 4 plus 1, we have 5. We have 8 plus 2, that's 10, plus 1, 11, which is equal to B. We have 8 plus 4, that is equal to 12, plus 1, 13, which is equal to D. So therefore, this binary is equivalent to this hexadecimal value. Alright, so that's the end of this module, the introduction to number systems and conversion of different number systems. So the next video will discuss on how we can add, subtract number systems or different numbers. Thank you.